Welcome to Year 1 Mechanics, where we look at Chapter 10, Forces in Motion. We're moving on from Suva equation to forces in motion. There will be a connection between forces in motion, which you will learn a very famous equation linking the force and the Suva. However, before we do that, in this lesson, we are looking into force diagram and force vectors. So we'll look into some basic forces. What are the forces? We're looking at mechanics. How do we calculate forces? How do we you know, measure forces? How do we work out forces in vectors? Right. So in mechanics, A-level mechanics, there are a few kind of forces you will need to get used to. Okay. I'm going to share my drawings, whether you want to copy it or you want to enhance it using your own drawing, feel free. But I'm pretty sure I'm quite confident with my drawing, sarcastically. So first of all, we know forces, the unit is Newton. Okay, so we know we use N for newtons. Okay, so the unit for force is a Newton. Right, so first one. Okay, so first diagram. We are standing on the ground. Okay, so when you're standing on the ground, it's actually levitating. No, it's actually not. Yep, now it's not levitating. Right, so when you stand on the ground, okay, there are two forces you need to know. The first of all is your weight. Okay, we use weight as W. Okay, W equals the mass times the gravity. So W equals mg. Okay, so weight is the force we're talking about. So your mass is in terms of kilogram. We'll talk about that later. Okay, so mass is the kilogram. We'll look into that more. Gravity is G, 9.8. We'll learn in Suva. And W is the weight. Okay, so the force version of your force version of your mass is weight. If you're 60 kilogram, then your mass is 60. But the weight will be 60 times G. Okay. Now, when you're standing on the ground, the fact that the ground is not collapsing, okay, the ground is supporting you, that force is called a reaction force. Reaction, okay, so we use R. Whereas reaction is a support force from the surface. Okay, so these two are very important forces that we'll be dealing with again and again and again and again. Reaction and weight. Okay, next one. Okay, next scenario. Okay, where we have a hangman. So what is a hangman? Well, you should know hangman. Um, the guy about to get executed. So still a smile because why do we die without smiling? Even though it's sad, but still see life as a let's see life as a journey. Anyway, so hangman. Okay, so this you can see the string here is loose. Okay, that means we're still standing on the ground. Okay, standing on a platform. Okay, before get executed. So where we has a different called hangman, where the string is taut and the person unfortunately has passed away. Okay, right. So we want to look into the difference between these two diagrams. Okay, so hangman. What force do we have in here? Same as the previous one, because you're standing on a platform, you still have weight and you still have reaction. Now the reaction actually comes from the ground. Okay, it comes from the ground reaction, but we normally put it on the top. So it's up to you where you want to put it. It doesn't matter where you put it. You can put it here or you can put it here. Up to you, but you can't draw both. Okay, so now what about when the person is hung? So when a person is hung, then we have tension pointing upwards. Tension. So we use T. Okay, tension from a string. Okay, and what else? You still have the weight. Okay, so what kills the person? Well, technically, you could say, it's the weight of the person kills itself. Because if the person has zero weight, okay, that means I don't know what. There's nothing in the earth that's zero weight. Even an atom has a weight. Anyway, if the person is zero weight, okay, imagine zero weight, no mass, nothing, then the tension wouldn't do anything to the person, because in here the fact that the person died is because the weight is bigger than tension. Okay, that's why. So anyway, so these are force when we look at tension. So far we've introduced a reaction, a weight, a tension. Okay, next, we have um, two more. Okay, so on a slope. Okay, on a slope, let's say 30-degree. Okay, doesn't matter. So you are standing on a slope. Okay, okay, hiking. Okay, so what forces are there on the slope? Well, on the slope, you still have reaction. Okay, but reaction comes from here, comes from the ground, perpendicular to the ground. Okay, perpendicular to the ground, reaction. And what else? You have the weight. The weight is acting directly downwards, the weight, towards the center of gravity, center of the earth. Therefore, it's vertically down. Oh, but reaction will be perpendicular to the inclined plane because the support force is always given to you perpendicular to the surface you're standing. Right. Next one more. We have a rocket. Okay, a rocket, and this US astronaut. Yay! Let's go to space. I don't know where we'll come back. Maybe I'll see you in a million years. Right. So in a rocket, okay, what do we have in here? Well, we first of all we have air resistance, right? As we're shooting upwards, we got air resistance. Okay, and then we have the weight of the rocket, okay, and the body and the person, and also we have a thrust pointing upwards. Thrust, okay, means like fuel pushing you up. That burst of speed, thrust. Okay, in rocket. Right, one more. What about if you're jogging? Okay, if you're jogging, I don't know how to draw a person jogging, but I'll try my best. Draw some motion lines. Ooh, very quick. Okay, so running. Okay, jogging. So, what are the forces on a person jogging? Well, first of all, you still have the weight directly down, and you still have reaction upwards. Now, again, you can put it on here, but personally, when we draw forces upwards, we try to draw it on the opposite side of the diagram so that we know downward forces are here, upward forces there. But it doesn't matter. We'll fine tune these details later. What else? When you run, you got friction. Okay, friction. Now for friction, we use small f. Okay, so these are the forces that we have to know, right? Well, we'll dive into it a bit more later, one by one, more about, not about the hangman and the rocket, more about the inclined plane and this one. Right, okay, so let's have a look. Okay, some theories. Newton's first law of motion states that an object at rest will stay at rest, and then an object that's moving with constant velocity will remain at a constant velocity, at that velocity, unless an imbalance force acts on the object. So a good example will be, for example, a space, in the space, outer space. When you push someone, now why does a person need to have a tether attach them to the spaceship when they travel around space? The reason being is, if they fall out of a rocket and they without a tether, if someone pushed them out, then they will forever be traveling that direction with the same speed, and they couldn't stop it because there's no resistance, there's no friction. Okay, so what would kill them? Let's say a person wandering around space. Okay, here's a space rocket. Okay, here's a space rocket. And then this person. No, actually, it's not dead yet. So, set face, flying with a spacesuit. Okay, there's no tether. Okay, there's no strength in there. Okay, so it's being pushing upwards. So what will kill the person? Well, he can't stop because there's no friction. He can't whatever, he can try to swing his hands or legs, but it won't stop him. What kills him is maybe one day, million years later, when he maybe travels to another planet, let's say this Jupiter or something, Mars. Actually fly quite far away. Mars, okay? The gravity around Mars will pull him into it, and then until he crashes into something, then he will stop traveling at that speed. Otherwise, okay, if there's no other force stopping it, the person, it was still moving at that speed. But on Earth, that doesn't apply to us because when we run, when someone pushes you, you will stop because of the friction on the ground or air resistance. Okay, but you can think of it like on ice surface, icy surface. When someone pushes you, it's harder to stop. And imagine the friction is minimum, nearly zero. It's impossible to be zero friction. Even ice has some kind of friction, but just very, very minimum. But imagine a surface with zero friction. If someone pushes you and there's no air resistance, you're actually moving in that direction forever and ever and ever and ever. Okay, and you can't stop it. But is this important? Not really. Okay, but it's in terms of mechanics, we do have to teach you about what kind of some basic physics we'll talk about. Next one, resultant force. Resultant force is the overall force acting on the object. An object will accelerate in the direction of the resultant force. So, if the forces on an object are balanced, then we would say the resultant force equal 0 Newton. Okay, so 0 resultant force. Well, what does that mean? That means upward forces, upward forces will equal to downward forces. Okay, we also have leftward forces will equals to rightwards forces. Okay, rightward forces. Okay, so now what does that mean? Now imagine there's a lot of theory in here today we'll talk about because it's all about theory for this chapter so far. Okay, so imagine that's you. Okay, maybe your dad wants you to help him with something. Okay, with 10 Newton pulling. Okay, and then mom say, "Oh, come and help me somewhere." Okay, and then pulling you 10 Newton. Okay, um, next, maybe your sister wants you to help. Oh, can you help me with some homework? 5 Newton. Okay, and then your dog say, "Oh, come and run with me." 5 Newton. Then, okay, from here, it looks like the person is about to get delimbed, the limbs taken out. Sorry, not horror movie. Anyway, imagine, okay, so now in here, are you moving anywhere? After all these forces, you're not moving anywhere because upward forces, you can see 5 Newton balanced with the 5 Newton underneath, and forces left and right are balanced. So if all these forces happened on you at some point, ultimately, you're not moving anywhere. You stay at the same point because the forces are balanced. That's what we call resultant force is 0. Okay, so this one, okay, resultant force equals 0 Newton. Okay, absolutely balanced. So we call this equilibrium state. We'll talk about this word a little bit more later. Equilibrium state. Okay, equilibrium state. Right. So what if you have another one in here. This is pulling 10 Newton, this pulling 8 Newton, this pulling 3 Newton, this pulling 2 Newton. Okay, is the resultant force 0? No, because 3 is greater than 2, 10 is greater than 8. Now, could you guess what direction will you be finally moving at? It's not 0. You'll be moving, okay, so you'll be moving in that direction. Okay, because 10 is greater than 8, that means you're moving to the left. 3 is greater than 2, you're moving up. That means left up means top left. Okay, right. What about this? If someone pulling you that direction and someone pulling you not actually, hang on. That direction? Oops. Is it resultant? Resultant 0? We don't know yet. We'll find out later. We actually will know later in year 2 mechanics. Okay, when the forces are diagonal. So far, this will suffice. All right. So we can resolve resultant force in 2 directions. Okay, one is called the parallel. Let me type it up because my writing has not been the best recently. Not recently. It's always been the case. Right. Oops. Okay. So parallel. Oops. Parallel to direction of motion. Right. Or we can say x direction. Another one is perpendicular to direction of motion. Or we can call it y direction. I call it y direction. Okay, right. So we have a look into what do we mean by that. Okay, right. Example: 4 forces have exerted to an object. You can see 5 Newton, 30, 40, and 30 in here. as shown in diagram. Work out the resultant force in the horizontal direction. So this talk about the x direction. So the resultant force, we use RF for resultant force. The resultant force on x is 30 equals 30 minus 30. Because resultant force means what's the verdict. Okay, so horizontally, we've got one pulling to the right 30, one pulling to the left 30. So 30 minus 30 is 0 Newton. Okay, resultant force on y direction, okay, up take away down equals 35 Newton upwards. Okay, so you can put some arrows in there. So that's right, take away left, up, take away down. Okay, so yeah, right. Example in here, find the resultant force in the two directions. Two directions surely means x and y. So if we look at the x direction, okay, so question A, the resultant force in x direction, we have 2 plus 3, so that's right, take away left, which is negative 2 Newton. Or negative 2, as I said, force is a vector. That means force has direction. So negative 2 Newton, okay, it means 2 Newton to the left. Okay, so we are doing the right forces, take away left forces. What about resultant force on the y direction? Okay, you have upward force, 4 minus 6, which is negative 2 Newton again. So that means this is 2 Newton downwards. We tend to take right as positive and take up as positive as well. So that's why we do up, take away down, so we get negative 2. So part B, find the size and direction of the resultant force. So now, if I combine the resultant force in x and resultant force in y, so I combine the resultant forces x and resultant forces on y, what will it look like? The particle in here, that becomes 2 Newton left and then 2 Newton, 2 Newton up. Sorry, 2 Newton down, 2 Newton down, 2 Newton down, right? So where's the final resultant force? The final will be here. So this is the overall resultant force. Okay. So how do you work out the size of this? So size. So the size, if we move this force to left hand side, that force a right angle triangle, because if you look at this side, this becomes a right angle triangle. So to do the calculation, what we'll do is we are going to draw a right angle triangle like this. 2 Newton here, 2 Newton. We just sort of rejuggle the 2 Newton left hand side in here, and that's the resultant force. This is the overall resultant force. I use blue just to color code it for you. So the RF equals Pythagoras 2 squared plus 2 squared square root. So 4 plus 4 is 8, so it's 2 root 2 Newton. Okay, angle theta. So tan theta equals 2 over 2. So theta equals 45 degree. So the size is 2 root 2 Newton. Direction is 45 degree below the horizontal. That's how we describe the angle, because it's underneath the horizontal. It's underneath in here. Okay, it's just pointing downwards. Okay, right. Moving on. Okay, practice question 1. Okay, given that this particle is stationary, that means all forces are balanced. Okay, work out the value of P and Q. Now, if you struggle with this, all forces balanced means up forces equals down, left equals to right. So you can think about that. Okay, and question 2, similar to what we did just now in the example. Pause the video, have a go at practice question 1 and 2. When you're ready for the answer, you can press play. Here are the answers. Question 1, quite fairly simple. Upwards equals down, P equals 20. Okay, Q, right, Q plus 15 equals 35, so Q is 20. Okay, question 2 is slightly more complicated, but resultant force in X will be 45 take away 20, in X with 15 take away 35, which is minus 20. That means 20 to point to your left. Okay, you can just leave it as minus 20 because minus usually people know is left side towards the left. Resultant force to the Y, 45 take away 20 is 25 Newton upwards, so it's positive. To work out the size of the overall, the size is the Pythagoras, do the minus 20 squared plus 25 squared, you get 32. To find the direction, okay, you can draw this little force arrows. Now, the resultant force in X is 20 pointing to left and 25 pointing upwards. So you can guess the final resultant force will be pointing in the somewhere middle direction. Okay, and then well, if you move the 25 Newton line to the left hand side to form a right angle triangle, you will see 20, 25 in here, and we usually work out the angle between the x-axis, between the horizontal. So that's what, if you're wondering why theta is here but not here, okay, because it's easier to describe theta when it's connected to the x-axis. Okay, so 25, 20 to SOHCAHTOA, you get 51.3 to describe the direction. We say 51.3 degree above the horizontal, because if that's horizontal line is horizontal, then a resultant force is going above 20. Okay, right. So let's carry on. Forces have direction, therefore we can naturally write them as vectors, either in INJ notation or as column vectors. We have sort of learned similar stuff in chapter 11 in pure maths, pure one. Right. You can find the resultant of two or more forces given as vectors by adding the vectors. Now, underline or highlight this. When the forces are given in vectors, you can just add them together. Okay, so you can write simple words in here if you don't understand what this means. It means if the forces are given in vectors, resultant force is the sum of the vectors, or simply add the vectors. Example, okay, the forces 2i plus 3j, now they're I and j form, so hopefully you do remember I means horizontal, okay, oops. So I and j, right? So hopefully you do remember that. The forces, there are three forces, 2i plus 3j, 4i minus j, and minus 3i plus 2j, and ai plus bj. Action object, which is in equilibrium. Okay, in equilibrium. Equilibrium. It means resultant force in x and y directions are 0 Newton. That means balanced. Equilibrium means balanced. So we can first of all work out the resultant force. So resultant force, okay, equals to, so let's write each of them as a column vector, 2, 3 plus 4 minus 1 plus minus 3, 2 plus a, b, which equals, if you simplify it, 2 plus 4, 6 minus 3 is 3, 3 plus a, 3 minus 1 is 2, 2 plus 2 is 4, 4 plus b. And what do we know about this resultant force? Equals 0. So what it means is 3 plus a equals 0, and 4 plus b also equals 0. Therefore, a equals to minus 3 and b equals to minus 4. Done. So to find the resultant force of these vectors, simply add them up together. All right. So no shenanigans like before, x and y. Just put them as a vector, just add them all up. Okay. So example, one more. The vector is due east. Vector I is due east. We know that I is due east means that way. J is due north. That's always the case. A particle begins at rest at the origin, is acted on by three forces, again vectors. Find the resultant force. So to find the resultant force of vector, we simply add them together. 2i plus 1j, you can write as a column vector, plus 3 minus 2, plus minus 1, 4. Now, personally, I prefer to do the calculation in column vector form. The reason being is just simpler to read. Okay, so if we 2 plus 3, 5, 5 minus 1 is 4, 1 minus 2 is minus 1 plus 4. Can't do the mental maths. 1 minus 2 plus 4 is 3. Okay, but we have to write I in j form, so which equals to 4i plus 3j Newton. Okay, part B, work on the magnitude and a bearing. Right, so you've actually learned how to work at the magnitude and bearing of vectors. So ignore it being a force, but you've learned how to work out the magnitude bearing of vectors. So to work out the magnitude bearing, we can first draw the vector. Okay, so if there's a particle, 4i means 4 to the right and 3 up. Right, so that's 4i plus 3j. Actually, I like to put a 4 in here. And where's the resultant force? Resultant force would therefore be here. So that's the resultant force. That's the overall resultant force. So magnitude. The magnitude we have learned two straight lines means magnitude, okay, like a bar. So 3 squared plus 4 squared, you should know the 3, 4, 5 triangle, okay, 5. And then to work out the bearing, so let's work out theta for now, okay. Theta equals inverse tan of 3 over 4, which if I do it correctly in my head is 36.9. Yeah. There's actually quite a common angle in mechanics for some reason. Okay, so what's the bearing? Okay, if you remember bearing, so bearing measures from north. So if you think about, that's the north line here. Okay, so 100. That's the north line, right? And then that's resultant force. If we draw the triangle out again, in here, we'll draw a little triangle. We've worked out this theta. So where's the bearing? Here. The overall. That's the bearing. Okay. So how do we work out bearing? Well, oh, sorry, actually, wrong. I was wrong, sorry. Bearing should be north line to the resultant force just here. Sorry, my bad. Bearing is only from the north line to the blue line, to the force itself. That's a bearing. Bearing measures from north to the force. So bearing equals to 90 degree minus 36.9, which is 53.1 degree. Okay, technically it should be 0.53. Okay, right, if you're happy with this, have a go at this question, these two questions, pause the video, have a go with the question. When you're ready for the answer, you can press play. Here are the final answers. Okay, question 3, quite simply, to find resultant force, add them up together. Okay, element vector, you got I and J, I plus J. Okay, yeah, right. Question 4, slightly more complicated, but actually not quite. Resultant force of a vector, add them all up together. 6, 4, find magnitude, do the Pythagoras of the I and J term. And part C, find the bearing. The bearing is from a north line, so that's the angle. But to work out that one, let's draw a right angle triangle. That's a theta. And so you can work out theta being 33.7 degree. So the bearing is 90 minus that, which is 56.3, or technically accurate 0.56 degree. If you really want to be technical about bearing, it's always 3 digits. Yeah. Okay. And that's the end of chapter 10.1 and 10.2, a simple introduction to mechanics and forces and motions.